Hello and welcome back to my channel. In last few episodes we have been exploring statistics for chemistry, to be more precise statistics for analytical chemistry, and so far we have discussed in the first episode of this series the R square in the linear least squares method, random errors and the distribution and nature of distribution of random errors to be normal or Gaussian distribution, and a third episode statistical treatment of these random errors. So I have focused a lot on errors, random errors, and in today's episode 4 we will discover some applications of data treatment, particularly confidence interval, CI, etc. But before I go for CI, as I mentioned that we are giving a lot of emphasis on error, it's a quotation from, of course, a judicial system. It is a more serious error to convict an innocent than to acquit a guilty, right? And this is a very famous quotation, but quoted here in this book. Actually, this is my reference, the only one. My concepts, my study, my reference, my problems, all are taken from this book. Fundamentals of Analytical Chemistry, Fowler and Crouch. So, what do you want from our statistical treatment of data? Suppose we want to have some quantity value of some entity from a population. Population means a huge collection of data or measured data values, or huge collection of, you can say, the biological or physical samples, chemical samples, and if we can measure so many and all the samples, physical samples of that set or population, that would be the best possible thing, and finally to get an average, and we can safely say that that population mean or average is the actual value of the quantity that I want. But practically it is not possible, mainly because of the reason that the population contains a huge number of data, huge number of measurements to be made, which is not possible. So what we do, we take a smaller subset from the whole set, which we call sample, not physical sample. In statistical vocabulary, sample means a smaller collection of measurements or data or physical samples. So we try to find the mean of this sample, mean of some quantity from this sample, and we interpret that mean to be the population mean. Can you interpret that? So how good it is? That question comes initially, that the sample mean, how good it is, or in other words we can say, keeping in mind the target that we want the population mean, the exact value. So in other words, how close is it, the sample mean, to the population mean? Close means either from left or right, that means it may be slightly lower or slightly higher. That means, in other words, we can frame the question that, okay, can we find at least a range that covers or brackets the population mean? Range, is it possible? And even if it is possible, how much sure I am about that range? That means in terms of probability, how probable it is that the population mean would be in that range. And then lastly, how big the sample has to be. That means, okay, if I cannot go for the whole lot of sample, physical samples of the population, I have to go for a smaller number of samples, right, physical samples. But how many? Minimum how many I have to take, which I can call that the big enough, right? So these are the questions. Or we can reframe the last question, that we have to determine the number of measurements required to ensure that experimental mean falls within a certain range with a given level of probability. So now ready we are to define what really confidence interval means. So the definition goes like, the confidence interval for the mean is the range of values within which the population mean mu is expected to lie with a certain probability. So the mu is expected to lie within a range but with certain probability. That range is called confidence interval, right? Obviously, for common sense, if you require high probability, then you have to compromise with your interval. That means the interval would be wider, broader, and if you want to make it narrower in another way, then the probability would be less. Okay. How do we say all these things? For example, we might say that it is 99% probable that the true population mean for a set of potassium measurements lies in the interval 7.25 plus minus 0.15% potassium. Thus, the probability that the mean lies in the interval from 7.10, that means 7.25 minus 1.15 to 7.40, that is 7.25 plus 0.15. So within this range it will lie, and the probability is 99%. This is the way how we present the thing. And here the probability, that is we sometimes calls confidence level, and expressed as a percentage. Here you see is 99%, right? So this is the way. Now, what are the factors that this confidence interval depend on? It depends on primarily the standard deviation of the sample, statistical sample, right? Standard deviation, and in turn which is the measure of the standard deviation of the population. So which may not be the case always. That means the standard deviation of sample, which we call S, and standard deviation of population, which we call sigma. So S may be a good measure of sigma, may not be a good measure. So that we will discuss in two different separate cases. Okay. So this confidence interval depends on this S value and how good this S is in terms of its representation of sigma. Okay. And next we will discuss in depth. Let us start with the very simplest one, single measurement. I have been given a population, but I will make just one measurement, and I want to say that what is that range, right? So in the earlier episode we have seen that a kind of variable transformation from x to z we have done in this way, that is x minus mu, deviation of the value from mean per unit sigma, right? That is we call z, and this is done because in that case if you draw the distribution, that means relative frequency versus z, and the curve would be the same for different Gaussian curves irrespective of the sigma value, provided you plot against z, not x, right? And remember that z can have both plus minus values, so x minus mu equal to plus minus z sigma, therefore Ci for mu would be x plus minus z sigma. So we will get Ci for mu x plus minus z sigma. This is the working formula. But single measurement, rarely we do that. What we do, we estimate the true mean. We don't estimate the true mean from a single, but instead we use the experimental value of mean x bar of n number of measurements as a better estimate of mu. Okay. So in this case we have to change slightly, that x would be replaced by x average and sigma would be replaced by standard error of the mean, which is defined as sigma by root n. So sigma is replaced by sigma by root n and x is replaced by x average mean. So finally we get for n measurement, Ci for mu is x bar plus minus z sigma by root n. Okay. Now as I mentioned that we will have two cases where the first one is that S is a good measure of sigma, or we know sigma of the population, right? So what happens in that case? If we make a single measurement of x from a distribution of known sigma, we can say that the two means should lie in the interval x plus minus z sigma, as I have mentioned already, with a probability, and that depends on z. So this z depends on probability, or probability depends on z, whatever you say. Suppose, for example, this probability is 90% for z equal to 1.64. 95% for z equal to 1.96 and 99% z equal to 2.58. So fortunately, this z value we have already have a complete table. But how do we get that table? What really it gives it? So here is a table for different level of confidence level probability, and the z values are different, and more the probability, more the value of z, and hence more the value of the range, right? Plus minus z sigma. So z more means more range. But where from it comes? We have already seen actually. It comes from the area calculation. This is the distribution, relative frequency versus z, and if you integrate within the limit of plus minus 0.67 sigma, z equal to plus minus 0.67 sigma, then the area, and area is nothing but the probability, which comes as 50%. So you see here 50%, it is 0.67. Similarly, if we go for a higher probability 80%, then you have to naturally take the higher range, and that is plus minus 1.28. So plus minus 1.28, that gives you 80%. And similarly, if you are interested in 95%, then you have to get z value 1.96, and so on. So z is at our hand. Okay. Now the number of measurements instead of single measurement. If we increase the number of measurements n, but the more the value of n, narrower would be the range. Of course, relative size of the confidence level decreases, but it decreases square root of n, not n, but square root of n. Anyway, it decreases. So if you take more n value, the relative size of confidence interval decreases. That's fine. Now I'll go for a few demonstration calculating CI, what are needed for my data calculation, and demonstration 2, calculating number of measurements needed to achieve a given CI. So n, what would be the minimum n value that I have to take for getting a desired level of range, right? CI. Let us see. So here is a problem. It goes like, determine the 80% and 90% confidence interval for A. The first entry 1108 milligram per liter glucose. In earlier example we have seen, and I will also see here. And B, the mean value, which is also given for month 1 in the sample example. So you are a doctor, you are taking samples of a patient a number of times in month, and for a few months you have taken the data for glucose measurement, diabetic patient. So this is that kind of example, and assume that in each part S, the standard deviation of sample, A19 is a good measure of sigma. So this is the first case that we are assuming that S is a good measure of sigma. So how do you calculate? So this was the example that 4 months, and every month a number of studies measurements have been done, and the average of this first month data is this one, and similarly for the second month is this one, and so on. Okay, and you can calculate the standard deviation of each month like this, 16.8 to 22.2. Okay. Now the formula is mu equal to x plus minus z sigma. So the first case is you are considering a single data, that the first entry 1108. Okay, so and the percentage or probability is 80% and 95%. So you can consult the table to get the Z value to be 1.28 and 1.96 for these two percentage. So you know sigma, you know now Z for two different probability cases, and X is that also you know 1108. So now you can just put the value to get two answers for 80 and 95% respectively, and it comes out 1108 plus minus 1.28 Z because 80%, and this is 1.96 for 95%, and this is the sigma value, I mean for the sample, So it gives you a range like this, right? So confidence interval is this. That means we can say that the probability is 80% that the true mean or the population mean would lie within this range. Okay, as we have already seen. Now from these calculations we conclude that it is 80% probable that mu, the population mean, lies in the interval 1083.7 to 1132.3. That means if you add and subtract this value to 1108, and similarly for the next one. Okay, so these are the first case. And now B, case B, where you are supposed to take that 0.005 value of S to be a good measure of sigma or the sigma itself. So in that case the formula change for 7 measurement, so you are using 80%. Now the formula is Z sigma by root n. So Z is 1.28 again, 19 is sigma, but root n is okay 7, because 7 measurements were done in the first month, right? So the result comes like this. So sorry, this is the case we are discussing where instead of one measurement we have gone for more than one measurement, that is 7. So let us summarize the results, then you will get it more clearly. So these were the values for a single measurement. These are the two ranges for the probabilities corresponding 80 and 95%. These were the range. So as you see, if you increase the range of probability 80 to 95%, then the range goes higher. It is 1070 to 1145, a wider range compared to this one, 1083 to 1132. So that is quite obvious. But what happens if I go for from single measurement to 7 measurements? These both the cases 80 and 90%, 95% cases, the value improves. That range become narrower compared to this one, and this one is narrower compared to this one, and again from left to right 80 to 95 the range is wider in the right hand side. That's okay, as we have seen earlier. Here also it is true, but as you go from top to bottom the range decreases, right? Because why? Because you have taken more than one measurement. Fine. Now the same results here, I am repeating here, but the case is that another problem that okay, for 95% CI we have seen that the range comes out like this, plus minus 14.1, right? This is the average, first month average. Now if you want this to be plus minus 10 only, but the same probability 95%. So you want your confidence interval to be within this range. Okay. Then how many measurements you have to make? We have done with 7 and you have got this result plus minus 14. And we have to improve still more in terms of number of measurements to get even a narrower range, plus minus 10. So how we can do that? Very simple. Your this formula Z sigma by root n, this should be equal to plus minus 10 here, plus minus 10. So x bar, which is 1100.3, and Z sigma by root n is nothing but plus minus 10. So plus minus 10. Now Z is known, for this percentage 95%. 19 is known, the sigma value, and n is unknown that you want to measure. So from this calculation you can find that root n is 3.724 and n comes as 13.9, rounded to 14. So what we conclude, that we thus conclude that 14 measurements are needed to provide a slightly better than 95% chance that the population mean will lie within plus minus 10 unit of glucose of the experimental mean. So we can improve the range by this way. Okay. Now case B, that where the confidence interval sigma is not known. It's not a good measure. S is not a good measure of sigma. Okay. So again the formula is very similar, but only difference is that sigma is replaced by S. That means population standard deviation is replaced by sample standard deviation S. And we define, instead of Z, we define a new term T, x minus mu by S. Only sigma is replaced by S. Well, this is for single measurement, and for n measurements, this again it is very similar to this one, and we can say that x is replaced by x average and S is replaced by S by root n, like the previous one. This is called the T statistic and often called student's T. Student was the name used by W.S. Gossett when he wrote this classic paper. Okay. So finally, as we have replaced Z by T, x by x bar, S sigma by S, and finally S by root n. Similarly for Ci, the final formula would be very similar, but again some changes would be there. Sigma is replaced by S and Z by the new term T. So we get Ci for mu is x bar plus minus Ts by root n. Okay, Ts, it was Z sigma, now it is Ts. Now Z goes parallel to T, and you have to carefully see that T depends on what and what. First of all, like Z, it depends on the confidence level, that is the probability, what probability you want. But here something extra comes, the number of degrees of freedom, because that was needed for S calculation, which was not needed for sigma calculation. The sigma and S calculation, they are slightly different. And of course, T approaches to Z as degrees of freedom becomes very, very large. That we will see. So for a table like Z table, here we have a T table, but here the extra factors are that degrees of freedom, right? So for 80%, the T value is 3.08, but for degree of freedom 1. But if you go on increasing degrees of freedom, it all decreases, and finally it converges to the 1.28 value, which was the Z value for 80% probability, and that becomes when degree of freedom goes to very large. Okay. So now let us see quickly a problem. A clinical chemist obtained the following data for the alcohol content of a sample of blood of percentage alcohol 0.084, 0.89 and 0.79. Calculate the 95% confidence interval of the mean, assuming that A, the three results obtained are the only indication of the precision of the method, and that B, from previous experience on hundreds of samples, we know that the standard deviation of the method is 0.005% and is good estimate of sigma. So we are observing here both the cases the same problem, that when it's not a good measure of sigma and when it's a measure of sigma. Though if you carefully note that in the earlier case the S value is already, we have got the same 0.005%, right, S value, and the difference is in case B is that we are assuming this S value to be a good estimate of sigma, and that's the difference only, and how it creates a difference in result you see. So this is the formula. We have to calculate this time the S, not the sigma, which was given in the earlier problem, but this time we have to calculate S by this formula, and for that reason we have to evaluate this xi square sum and xi sum whole square. So xi sum for three values is this one, and x square sum is this one. So these two are calculated, and now S is finally this value, and 3 minus 1 degrees of freedom, so 2 degree of freedom is 1, and that result comes as 0.005. Okay, interestingly, this is the case, the value we are assuming in the second case that will be a good estimator, but right now we are not assuming that, we are calculating it 0.005. And what is the x average? Okay, so this value divided by 3, that gives you the 0.084. Now from table we can get that T is 4.30 for 2 degrees of freedom for 95% confidence level. So we just now put the formula for 95% case, x bar plus minus Ts by root n. So x bar is this one, T is 4.30, S is this one we have calculated, and root 3, and that gives you 0.084 plus minus 0.012% of ethanol. Okay. And the case B, where it is assumed to be a good estimator, this S and sigma, in that case it is Z sigma by root n, x plus minus Z sigma by root n. So again you just put the value Z for this percentage 1.96, sigma is 0.0050 is given by root n, and this time we get the range or CI is 0.084 plus minus 0.006%. Okay. But note that a sure knowledge of sigma decreases the confidence interval by a significant amount, even though S and sigma are identical, 0.005. In the earlier case, when it was not good estimator, it was 0.012% plus minus, and here it is 0.006%. So the range is better one. Okay. So thanks for watching. Our next video would be coming soon, and that will be exploring statistics 5, concepts and applications through problems and Excel spreadsheet, part 1. Till then, please keep on watching, do subscribe, and encourage your friends to subscribe.